All right, we are starting to talk about the sine and cosine functions in 7.3. And we start to make the jump to the unit circle as we do this. And I think as we look at the sine and cosine functions, a really good idea as we start is to take a look at their definitions. We've seen this before. This is stuff we know, but it's good to remind yourself of when we talk about an angle's sine value, to get back to the fundamental concept of what it is. Okay, the idea comes from a right triangle where we have one of the angles, in particular one of the non-right angles in a right triangle. And from there, we can label each side as opposite. That's the one on the other side of the triangle. Adjacent, that's the one next to. And the hypotenuse, which is always the side that's opposite the 90-degree angle. An angle's sine value is always the ratio of its opposite side to the hypotenuse. Okay? And because the hypotenuse is the longest side, we are guaranteed that the denominator of that fraction is bigger, and therefore sine values must be less than 1. Cosine value of an angle is its adjacent side divided by the hypotenuse. And the same thing holds true that it's got to be less than 1. Okay? But that's what those two values mean. In a right triangle, it is that angle's opposite side divided by the hypotenuse. That's a sine value. The adjacent side divided by the hypotenuse. It's all about a ratio of side lengths. Now let's jump to the unit circle. Okay, let's say we pick a point on that unit circle. Okay? X and Y. Okay, that point forms an angle. Okay? Now if we want to think of that angle as theta, we can actually break this down a little bit more. All right? The coordinate, if we relate this to a right triangle, the coordinates of the point are x and y. Okay, again, if I want to get to that point, I would move x units to the right and y units up, and there we go. Okay, the hypotenuse is the radius of the circle, and that's always 1, okay, because it's a unit circle. We've defined that the radius is 1. So the coordinate points, along with the radius, kind of form this right triangle that includes angle theta. Okay? So now if we think about that right triangle, and remember the sides of the triangle are the same as the coordinate points that describe the location of that point on the circle. Okay? The sine value of theta, which is still the same thing, opposite over hypotenuse, we're just calling the opposite side and the hypotenuse by some different names. The sine value of theta is y over r. And likewise, the cosine value is x over r. But wait a minute. This is a unit circle, r is 1. That means that the sine value of theta is y over 1, or just y, and the cosine value is x over 1, or just x. All right? So when we think about the coordinates of that point and the angle that it forms, there is a very, very significant relationship. The x-coordinate of that point is theta's cosine value. The y-coordinate is theta's sine value. Okay, start to equate those two things on a unit circle. X with cosine and y with sine. You could say the same thing down here, that if we wanted to find any ordered pair on the unit circle, if we knew the angle that was associated with that point, That would be its sine and its cosine value. Again, cosine is equated with x, sine with y. So if the terminal ray of an angle, remember it's formed by two components, the initial ray, which is always right here and never moves, and then the terminal, we know this terminal ray goes through the point -3, 2. Let's go -3. So we got 3 units to the left, 2 units up, and let's put that point. Okay, it's saying that the terminal ray, or the terminal side, goes through that point. Okay, notice doing that forms an angle. That terminal side with the initial side forms an angle. All right. Now this is a little bit different, and this is why I really wanted to get back to right triangles to think about sine and cosine, because this is the idea of the functions. Is at any angle we can evaluate its sine and cosine function. Now this angle is bigger than 90 degrees, so it could not show up in a right triangle, but it still has a sine and a cosine value, and in fact we want to find them. And it's still based on x, y, and r. Remember in this whole process here, okay, that when we're dealing with this coordinate grid and how we'll set this problem up, sine is y over r and cosine is x over r. That doesn't change even though the angle is bigger than 90 degrees. Now over here, I can get kind of fancy and I can draw in a right triangle. And in fact, due to the coordinate points, I know that that side of the triangle is 2. And this side is really 3, but I'm going to call it -3 because it was 3 units to the left. That's actually significant. I need to factor in that -3. It's kind of weird to call a side length negative, but that is what it is. We need the negative sign. And this hypotenuse right here from 0, 0 to -3, 2, well, that's r. Now, if I use the Pythagorean theorem, without too much effort, I can figure out r. R squared is 4 plus 9, which is 13. So r is the square root of 13, and now if I think about this, okay, with the, components of this right triangle that I have, I know x is -3, y is 2, and r is the square root of 13. So first, if I think about theta's sine value, and that's y over r, well, y is 2, and r is square root 13. If I were to rationalize that, I'd get 2 square root 13 over 13. Okay, that would be its exact sine value. I could just evaluate that in a calculator to get a decimal approximation. Cosine of theta is x, which is -3 over r, which is square root 13. Once again, I'll rationalize. And there is angle theta's cosine value. Okay, a little bit different when that angle's over 90 degrees, but it's still all about x, y, and r. If theta is in the fourth quadrant, well, let's just draw a terminal side in quadrant 4. So this would be angle theta. The fact that it's in quadrant 4 means it's somewhere between 270 and 360 degrees. I know the sine value of theta is -5 over 13. And again, as always, theta is y over r. Okay? I want to figure out from that information theta's cosine value. Well, let's say I pick a point on that terminal side, and I do this whole right triangle thing again. I don't know what x is. I know y is -5, and I know r is 12. Again, I can use the Pythagorean theorem. Excuse me. Matter of fact, r isn't 12. R is 13. 13 squared is x squared plus -5 squared. Using the Pythagorean theorem again, and you'll see this will come up all the time. Okay, all the time. Just trying to figure out what the x component of this triangle is, which is going to have to do with its cosine value. It's 12. Well, now I'm in good shape because cosine of any angle that is drawn on a coordinate grid in this manner is always x over r. X is 12, r is 13. Problem solved. That angle, which again, I don't even know what that angle is. All I know about it right now, somewhere between 270 and 360. Based on my diagram, I think it's a little bit closer to 360. But its cosine value, I know, is 12 over 13. Just want to look at how we evaluate, and again, this is really coming back to the fact that sine values, associate those with y coordinates of points on the unit circle. Okay, any point on a coordinate grid that's on the unit circle, associate with its sine value. For example, 90 degrees is formed right if I drew that point. Okay, and I'm always thinking relative to the initial side. Okay, that point on the unit circle is 0, 1. If I draw on the terminal side, it forms a 90-degree angle. Because the y-coordinate's 1, that is 90 degrees sine value. All right? If we see something like 450, don't be afraid to use a coterminal. Okay, right away, subtract 360, and we see that, okay, wait a minute. Instead of 90, we're saying go all the way around again. We're still in the same relative position as 90, so the sine value of 450 is still 1. Okay? Pi is right over here. Remember, that's the conversion factor that we use so much, that 180 degrees is the same as pi radians. Again, I identify that point in terms of where pi is. I see the y-coordinate is 0. Therefore, the sine value of pi radians is 0. Okay? If we see a negative, remember that just means open up the opposite way, open up clockwise. Okay? Based on this relationship, 90 degrees is pi over 2 radians. So I just rotate clockwise, and there's the point I'm going to use. It's -1. Okay? Because the y-coordinate at that point is -1. Cosine, do the exact opposite. Just associate it with the x-coordinate. Okay? This point on the unit circle, -1, 0, forms a straight line with the initial side. Cosine of 180 is -1. Again, don't hesitate if you've got a huge angle. Use a coterminal. I subtract 360. That's right here. X value at 360 is 1. Okay? 3 pi over 2. Remember that pi over 2 is 90 degrees, so go 1 pi over 2. There's 2 pi over 2. And there's 3 pi over 2. X-coordinate is 0. Therefore, the cosine value at 3 pi over 2 radians is 0. Okay. That'll be all for Learning Target 7.3. The key points here, x, y, and r, particularly that cosine of an angle on a coordinate grid is x over r and the sine value is y over r. Very important to keep those ratios in mind. All right, we'll call it quits here. If you have questions, please be sure to ask those in class.